You ever look at a circuit diagram and just feel your brain kind of freeze up? You've got multiple power sources all pushing and pulling current at the same time, and it can just look like a total mess. Well, today we're going to talk about a really cool trick for that. It's called the superposition theorem, and it's basically a divide and conquer strategy for circuits. It turns that chaos into something totally manageable. So let's see how it's done. Okay, so take a look at this circuit. This is exactly the kind of thing I'm talking about. Over on the left, you've got a voltage source pushing with 20 volts. Then, on the right, you have a current source that's basically demanding a constant flow of 4 amps. The key thing here is they're both on, both active, and both messing with the whole network of resistors at the same time. And that leads us to the big question, right? With power coming from two different places, how on earth do you figure out the current flowing through that 48 ohm resistor, the one right there in the middle? I mean, with electricity coming from both directions, trying to calculate that directly, well, it looks like a real headache.
Visit youtube.com/avidsystem and don't forget to subscribe.
But what if? What if you didn't have to deal with both at once? What if you could just, pretend only one power source was turned on? You could solve that super simple problem, then do the exact same thing for the other source. That right there, that simple, almost elegant idea, that's the heart of superposition. All right, here's the official definition. Now, it might sound a little technical, but trust me, it's exactly what we were just talking about. It says that for any linear circuit, and that word linear is important, we'll come back to it, the total current or voltage anywhere is just the sum of what each source does on its own. It's really just about breaking a big problem into a bunch of little, easy ones. And this really lays it out perfectly. On the left, you've got this one big, complicated problem you have to wrestle with. But on the right, using superposition, you have two much simpler problems. You figure out what's happening with each source by itself, and then you just add the results up. Honestly, for circuit analysis, this is a total game changer. All right, so that's the theory, but how do we actually put it into practice? Let's break down the step-by-step method. Think of these as the rules of the game. And the process is beautifully simple and systematic. First, you pick just one power source to leave on. Step 2, you turn off all the others. Then you do your calculation for that one source. After that, you just repeat the whole thing for every other source in the circuit. And when you've done them all, you just add up your results. That's it. All right, but wait a second. That brings up a pretty big question, doesn't it? I said you turn off the other sources. What does that actually mean when you're analyzing a circuit? I mean, you can't just pretend they're not there. There are very specific rules for this. Okay, here's rule number 1. When you need to turn off a voltage source, you replace it with a short circuit. And all that means is you replace it with a plain wire, zero resistance. The best way to think about it is like taking a battery out and then just connecting the two terminals together with a wire. You're forcing the voltage in that spot to be zero. Now, for a current source, you do the complete opposite. You replace it with an open circuit. And that's exactly what it sounds like. You literally create a break in the wire. You just snip it. That way, you guarantee that zero current can possibly flow through that branch, which is how you turn off the current source. Okay, we've got the theory, we've got the rules. Now, let's actually put it to the test. We're going to go back to that original circuit and see this whole thing in action. So, for part 1, we're going to keep the 20-volt source active and turn off the 4-amp current source. And what's the rule for a current source? That's right, we replace it with an open circuit. So we basically just snip the wire right where that source was. Now that the circuit is much simpler, we can actually analyze it. So first, we figure out the total resistance that the voltage source sees. Once we have that, good old Ohm's law gives us the total current coming out of the source. But that current splits, right? So we use the current divider rule to find the exact slice of that current that's going through our target 48 ohm resistor. And that works out to 0.208 amps. All right, let's write that number down and save it for later. Okay, on to part 2. Now we flip the script. We're going to keep the 4-amp current source on and turn the 20-volt voltage source off. And remember the rule for that? We replace the voltage source with a short circuit. Just a plain wire connecting the 2 points, just like you see here. So in this new configuration, our 4 amps of current comes along, hits that junction, and it has to split. Once again, the current divider rule is our best friend here. It lets us calculate exactly how much of that current goes down which path. And when you run the numbers, you find that 0.8 amps goes through our target resistor. And boom, that's the second piece of the puzzle. Okay, we've done all the heavy lifting. We divided the problem, and we conquered each part individually. Now, All that's left is the best part, the easy, satisfying final step. We just add our two results together. And there you have it. We take the 0.208 amps from our first calculation, add the 0.8 amps from our second calculation, and we get a grand total of 1.008 amps. That is the actual total current flowing through that middle resistor. Problem solved. But hold on. Like any really powerful tool, you gotta know its limits. The superposition theorem is amazing, but it doesn't work for everything. And understanding this fine print is absolutely crucial if you want to use it correctly. So there are two really big rules to remember. First, it only works for linear circuits. We're talking about components like resistors, capacitors, inductors, things where the voltage and current have a nice proportional relationship. And second, and this is the one that trips people up, you cannot, under any circumstances, use it to calculate power directly. And why is that? Well, the reason is simple. Power isn't linear. Just think about the formula for power. P equals I squared times R. See that little squared on the current? That's the problem. Because you're squaring the value, the relationship is no longer linear, and the whole just add them up magic of superposition completely falls apart. So here is the absolute rule for calculating power. You have to find the total current first. In our case, that was 1.008 amps. Then you use that final number to calculate the total power. What you can't do is calculate the power from the first scenario, calculate the power from the second, and add them together. It will give you the wrong answer every single time. It's a super common mistake, so please be careful with that one. And that, in a nutshell, is the superposition theorem. It's more than just a calculation method. It's a way of thinking. It transforms what looks like one massive headache into a few simple, bite-sized puzzles. So the next time you're staring down a complex circuit, ask yourself, are you seeing a single, impossible problem, or are you seeing a few simple ones that are just waiting to be added together?
Thanks for watching.